Hello, dear students. Today we're going to talk about Chapter 6, Section 2, Covalent Bonding and Molecular Compounds, the relation between covalent bonding and molecular compounds. Let's talk about it. First of all, we must know what's molecule before we talk about molecular compounds. Molecule is a neutral group of atoms that held together by covalent bond. If a group of atoms, two or more atoms, bond together by covalent bond, it's called a molecule. Example, H2O, CH4, O2. These are all molecules. They are all made of a group of atoms that held together by covalent bond. When we say covalent bond, means these atoms, they all must be nonmetals. Molecules are made of nonmetals, okay? But when there is between a metal and a nonmetal, it's not going to be called molecule. We called formula unit, okay? In next section, we will talk about, which is called ionic compounds. Okay. Diatomic molecule is a molecule containing two atoms. If a molecule made of only two atoms is called what? Diatomic molecule. Di means two. Okay? When two atoms held together by covalent bond is called diatomic molecule. Okay? Okay, what's chemical compounds? Any compound in nature is called chemical compound. The composition of chemical compound is represented by chemical formula. So, to show the composition of a compound is made of what? And the basic unit of a compound we're going to represent by a formula. For any compound in nature is called chemical formula. Chemical formula indicates the relative number of atoms in each kind in a chemical compound by using what? Atomic symbol and numerical subscripts. For example, chemical formula of water or the composition of water. Water is made of H2O molecules. So the composition of water is H2O. Sorry, the chemical formula of water is H2O. So what does H2O tells us? Tells us that the water is made of two hydrogen and one oxygen molecules that held together by covalent bond. And for sodium chloride, table salt is made of what? Is made of a group of NaCl ions. Okay, that's it. So it tells us there are two hydrogen and one oxygen that held together by what? By covalent bonds. Here, there are types of chemical compounds. Okay. Here we're going to talk about types of chemical compounds. There are two types of chemical compounds, molecular compounds and ionic compounds. Here we're not going to talk about ionic compounds, and later we will talk about ionic compound. Today we're going to talk about molecular compounds. What's molecular compound? Is a compound but is made of a group of molecules. A group of molecules together makes a compound which is called molecular compounds, and the basic units are molecules. Look at here, this is what? Water compound, and water compound is made of a group of molecules. Okay, here the basic units are what? Molecules. H2O molecule is the basic units. Okay, a group of H2O molecules make a compound, make a water compound. And what's important here, it says molecules are held together by covalent bond. We said that here these molecules, H2O, is made of water and is made of an oxygen and two hydrogens, but the bond between oxygen and hydrogen is what is covalent bond. Means the atoms held together by covalent bonding. Okay? So how do you represent composition? The composition of molecular compound is represented by molecular formula. Okay, we call molecular formula. Shows the types, numbers of atoms combined in a single molecule of a molecular compound. For example, molecular formula for water is H2O. What does it tells us? It tells us the type. We have hydrogen and oxygen. Number of atoms. How many number of atoms? We have 2 hydrogen and 1 oxygen in a single molecule. So a single molecule of water compound is made of 2 hydrogen and 1 oxygen. So we understand that if a compound is made of a group of molecules, it's called molecular compounds, and the compositions are represented by a molecular formula. By a formula we call molecular formula. But for any compound in nature, the formula is called chemical formula. Okay, for example, NaCl is a chemical formula, but it's not a molecular formula, because molecular formula, this term uses only for molecular compound, but chemical formula is used for every compounds in nature. Okay, that's it. Any compounds, later we'll talk about it. Formation of a covalent bonds. When two atoms, two nonmetals, they get together, they form a covalent bond, isn't it? Two nonmetals together, when they get closer, they share their electrons and it makes a covalent bond, isn't it? Here in this slide, we're going to talk about the steps, how atoms, they get closer, what will happen when they get closer, what will happen when they share electrons, when this covalent bond form. Okay, that's it. For that formation of covalent bond, we have an example of 2 hydrogen atoms. So this slide, here we just talk about this figure. We're going to explain this figure. This figure explains how a covalent bond forms. Okay, the steps. So we have 2 hydrogen. Here we're going to talk about how 2 hydrogen atoms, they bond to each other. First of all, you remember that nature favors chemical bonding. Means atoms, they like chemical bonding because most atoms have low potential energy when they're bonded. Okay, because we said when they bond, they're going to have less potential energy, they're going to be stable. So in the formation of hydrogen-hydrogen bond, 2 isolated hydrogen atoms separated by a distance large enough to prevent from them influencing each other. At this distance, overall potential energy of atoms randomly set at 0, as shown in part. We're going to talk about part A first. First of all, before bonding, atoms, hydrogen atoms, they're very far from each other. They don't affect each other. It means there's no attraction between them. At this time, they have potential energy. We randomly set at 0. We start from 0 to understand that when they get closer, how their potential energy decreases. So when they're far, they don't affect each other, they don't influence each other, and we set their potential energy randomly at zero. Okay, we say that their potential energy is zero at the beginning. What happens? As atoms get closer to each other, because they like to bond, they get closer to each other. Okay? Okay. They get closer. What happens when they get closer? Nuclei and electrons begin to interact. Look at this figure. Here, this paragraph is about figure 6. This is two hydrogen atoms. Basha? When first they get closer, between nuclei and valence electrons, what do we have? We have attraction. Nuclei and valence electrons. We have attraction on the valence electron and nuclei. There is attraction, means that causes atoms get closer to each other. And between nuclei, electrons, we have repulsion. And also between nuclei, we have repulsion. Between electrons, also we have repulsion. Okay? So what happens? Attraction, when atoms, they attract to each other, their potential energy decreases. Okay? Means attraction causes atoms decrease their potential energy. What about repulsion? At the same time, two nuclei repel each other, as we said. Two electrons, they repel each other because each hydrogen has one electron. That's why you say two electrons repel each other, which results in an increased potential energy. Repulsion causes increase in potential energy. Okay? At the beginning, okay, when they get closer, we have attraction, repulsion. Attraction between nuclei and valence electrons. We have repulsion between two nuclei and what? Two electrons. Okay? And attraction causes what? Attraction causes the potential energy be decreased. And repulsion causes the potential energy be increased. Okay? Then, what happens? When the atoms first sense each other at the beginning, when they first sense each other, what happens? The electron-proton attraction, nuclei means electron, nuclei has positive charge, is stronger than the electron-proton repulsion. At the beginning, attraction is more than repulsion. Okay? When attraction is more than the repulsion, the atoms are drawn to each other. They get closer to each other. When they get closer, because of attraction, high attraction means potential energy is lower. We said attraction causes the potential energy be decreased. So at the beginning, attraction is high. They get closer and their potential energy be decreased. This is explained here in part B. Here that at the beginning atoms, they have high attraction. This line explains the potential energy. Potential energy at the beginning is zero. Okay, we said randomly, but it's not zero. And we said at zero to understand how potential energy decreases. So at the beginning, they have high attraction to each other, and they get closer. And what happens? Their potential energy is lower, okay, by the attraction. Then the total potential energy continues to decrease because still attraction is more than repulsion. Attraction is more than repulsion. So this decreasing in potential energy is going to be continued. Eventually, a distance is reached until where? A distance is reached at which the repulsion between the like charges equals the attraction of opposite charges. Means this decreasing potential energy is going to be continued until the attraction and repulsion are balanced. When attraction and repulsion are balanced, what happens? At this point, the potential energy is at minimum and the stable hydrogen molecule form. Okay? So when attraction and repulsion are balanced, at this time, the potential energy is at minimum and a stable hydrogen molecule form means H2 here is going to be H2 means hydrogens, they're going to share their electrons at this time when the attraction and repulsion are balanced and they have minimum potential energy, which is minus negative 436. Okay, which is important. A closer approach of atoms, if they get closer, much closer, at the beginning attraction is high, repulsion also is going to be increased until attraction and repulsion are balanced, stable hydrogen molecule form. If they try to get closer, if they any closer approach, the repulsion is going to be more than attraction, and repulsion is going to be more than attraction. Atoms, they get farther from each other, or we can say when the repulsion is more than attraction, the potential energy is going to be increased again, results in a sharp rise in potential energy. Look, if they get much closer, a distance between hydrogen nuclei, here they get closer, and if they much get closer, what happens? The potential energy increases because repulsion causes the potential energy be increased. Okay, that's it. That's how a covalent bond forms between two nonmetals. Characteristics of a covalent bond. When the attraction and repulsion are balanced, a stable covalent bond forms. Okay, as we said, when here this figure part C1, attraction and repulsion are balanced, a covalent bond forms. The distance between two bonded atoms at their minimum potential energy, that is the average distance between nuclei of two bonded atoms, is the bond lengths. Look, guys, we say when two hydrogen atoms bond, as an example, the distance between nuclei of two bonded atoms is called bond lengths. But when we're going to measure at their minimum potential energy here, so we're going to measure the distance between two hydrogen atoms at this time when they have least potential energy. Okay, we're going to measure it here, not here. Okay, so we're going to measure the distance between nuclei of two bonded atoms when they have minimum potential energy. For hydrogen is 75 picometer. Okay, the distance between these two hydrogen atoms. Okay, bond energy. So this is H2, isn't it? So if you want to break that bond, how you can break? By energy. So the energy you need to break a bond and form neutral isolated atoms is called bond energy. Bond energy is the energy required to break a bond. A chemical bond forms isolated atoms, and when two atoms they bond to become isolated. In other words, look, the bond energy equals the amount of energy released in the formation of covalent bond. We said when two atoms they get closer, their potential energy is going to be decreased until they share their electrons. And this process, in the process of making a covalent bond, they lose their energy, isn't it? So the energy that they have lost in the process of covalent bonding, that energy equals the energy you need to break a bond. So the energy, the bond energy, look here, the bond energy equals the amount of energy released in the formation of covalent bond. For a hydrogen, negative 436 is the energy going to be released in the formation of covalent bond. The energy we need to break the bond equals that energy that they have released. Here, look, the bond energy of hydrogen is 436 equals the energy that the atoms they have lost in the process of covalent bond. Okay, formation of a covalent bond. So, but bond length and bond energy vary with the types of atoms that have combined. Look at the table 1. For example, the bond energy of hydrogen is 75, but for fluorine molecule between two fluorine atoms is 142 picometer, the distance between two bond atoms. Also bond energy, the energy you need to break hydrogen bond is 436. For fluorine is 159, means bond energy and bond lengths vary with the types of atoms that have combined. Okay? Then, when atoms they share electrons, sharing electrons allows each atom to have the stable electron configuration. What does it mean? So when atoms they bond, why they're going to have less potential energy? Because they're going to have a stable electron configuration. When an atom has a stable electron configuration, it's going to be stable. It's going to have the lower potential energy. Okay? So for example, hydrogens, they're going to, when they form a molecule, when they make a covalent bond, they share electrons in a covalent bond that have the stable electron configuration of helium. Look, there are two hydrogens. They share their electrons. Okay? When they share, both of them, they're going to have a stable electron configuration of helium. For example, this one, each hydrogen's electron configuration is 1s2. Basha? If you write when they bond. Now, 1s2 is not the electron configuration of helium. 1s2 is a stable electron configuration. So when atoms, hydrogens, they bond, they're going to have electron configuration of helium. They're not going to be helium atom because the number of, still they have one proton. So they are hydrogen, but their electron configuration is like the electron configuration of helium. And helium's electron configuration is a stable electron configuration. That's it, okay? That's why sharing electrons allows the atoms to have a stable electron configuration like a noble gas. Hydrogens, they're going to have the electron configuration of helium. They're going to be stable. Octet rule. Octet rule is important. Noble gases in group 18, they're stable. Why? Because they have 8 valence electrons in their last shell, except helium, which has 2, right? So that noble gas, they're happy. They're stable because they have 8 valence electrons. So other atoms, they want to be stable like noble gases. How? By having 8 electrons in their last shell. So this is called octet rule. Octet rule is referred to as atoms they gain. How atoms they're going to have 8 electrons in the last shell? By sometimes gaining, losing, sharing electrons to fill their valence shell with 8 electrons. Here look, these two transferring electrons, sometimes by transferring electrons. For example, atom A loses electron, the other one gains electrons. So A, if it loses 1 electron, it's going to have 8 electrons. It had 8 valence electron. What about this one? It has, by gaining, it has 7 valence electron. If it gains 1 electron, it's going to have both. They have 8 valence electron. Now, one loses, one gain. At this time, both they have 8 electrons and they're stable. because they have 8 electrons. Okay, how that happens? By bonding, isn't it? We said atoms, they bond to be stable. So when they bond, how they're going to be stable? By having 8 electrons in the last shell, by losing, gaining, or sharing electrons. Here, sharing electrons. Two nonmetals, like as we said, they're going to share electrons. Now both they are going to have 8 electrons in the last shell. Okay, except for some elements we're going to talk about. Now both they have 8 electrons, both are stable, like a noble gas. Okay, like two fluorine atoms. When two fluorine atoms they bond, each atom shares one of its valence electron with its partner. The shared electrons pair effectively fills each atom's outermost energy level with an octet of electron. Octet means 8. Look, there are two fluorine atoms. This is electron, this orbital notation. Both they have 8 valence electron, isn't it? Sorry, 7 valence electron before bonding. Okay, how they're going to be stable? By having 8 electrons. Now both they have 7, and they get closer to each other. Both they want electron, they want to gain. At this time, when both they like to gain electron, they're going to share, right? Both they have high ability to attract electrons. They're going to share their valence electron. By sharing 1 electrons, both they're going to have 8 valence electrons. They share what? They share their ampere electron. And this is going to be downward to not both have same spin state, because they're going to be shared between two atoms. But here, when we say these two electrons going to be shared, but in terms of orbitals, when you talk about orbitals, what their orbitals going to be changed? How their orbitals they going to be changed? Their orbitals, they are going to overlap. How? Look at these two orbitals. This is this orbital. Do you know that p orbitals, they have the mole shape? And this is the shape of the orbitals, how the electrons they move around the nucleus. This one, it has 1 electron. This one, it has 1 electron too. Look, now both they're going to overlap. Okay, this is overlapping orbitals. When two atoms they share electrons, their electrons will overlap. This process is called overlap. Now these two electrons are the electrons of both orbitals. Okay, and means this electron is the electron of this atom and this atom too. This electron is the electron of this fluorine and the other one. So means this electron, look, this electron moves around this atom, at the same time moves around another atom, because this electron is the electron of both. For the red one is also like that. Okay, now by sharing electrons between two fluorine atoms, both they're going to have 8 valence electrons in the last shell. Okay, that's it. Exception to the octet rule. Not all atoms, when they bond, they're going to have 8 valence electrons in the last shell. No. Elements such as hydrogen, lithium, beryllium, boron, these 4, when they bond with other atoms, they're not going to have 8 electrons. They will have less than 8 valence electrons. For example, in HCl, boron tetrafluoride. In HCl, look, hydrogen has bonded with fluorine. They have bonded. Fluorine is not the exception. It's going to have 8 valence electrons. But what about hydrogen? Now it has 2 valence electrons. We said octet rule means having 8 electrons, but hydrogen is an exception. It's going to have 2 electrons in the last shell, like helium. Okay. Boron also is going to have 6 valence electrons when it bonds with 3 fluorines. Okay. Later we will explain that. Elements such as phosphorus. Sometimes phosphorus and sulfur may have more than 8 valence electrons when they combine with the highly electronegative elements, fluorine, oxygen, chlorine. Look, if phosphorus and sulfur, if they bond with one of these three highly electronegative elements, fluorine, oxygen, chlorine, they're going to have, they can have more than 8 valence electrons. Here, phosphorus, pentafluoride, sulfur hexafluoride. Here, because phosphorus has bonded with fluorine, is going to have more than 8. Sulfur with fluorine, so because it has bond with highly electronegative, it can have more than 8 valence electrons. Here, for this one, phosphorus pentafluoride. Now, each fluorine has octet of electrons. What about phosphorus? 2, 4, 6, 8, 10. Now, phosphorus has 10 valence electrons. Okay? That's it. These are exceptions to the octet rule. Electron dot notation. An electron configuration notation in which is an electron configuration notation in which only the valence electrons of an atom of particular element are shown, indicated by dots placed around the element symbol, and the inner shell electrons are not shown. Look, electron dot notation is easy. Okay, how? We're going to just show the valence electron of an atom. It's an electron configuration notation. Only we show valence electron by dots placed around the element symbol. For example, for fluorine atom, the electron configuration of fluorine is 1s2, 2s2, 2p5. It has how many valence electrons? In the last shell, there are 7 valence electrons. So we're going to write this symbol of the atom, which is fluorine. It has 7, so we're going to write 7 dots. But please give each side 1 electron. Before any side, you give it 2. And now we have 4, 5, 6, and 7. Okay? So this is the electron dot notation of fluorine. For example, hydrogen. Hydrogen, it's in group 1. It has 1 valence electron. We place 1 dot around this symbol. Nitrogen, it's in group 15. It has 5, 1, 2, 3, 4. But for nitrogen, try to put the pair dots on the top. Okay, much better. It's up to you. Where do you want to put it? But you can't put like nitrogen like that. 1, 2, 3, 4, 5. That's wrong. Because you must give each side, right, left, top, and bottom, each side 1 electron before any, give 2. Okay? These are more examples. If it has 1 valence electron, how we're going to write X can be any element. If it's 2, 3 valence electron, like boron, how we're going to write the electron dot notation. Carbon it's 4. We can write like that. 1, 2, 3, 4. That's in group 14. Okay. Neon 8 dots. 4 pairs, right? Look, main group elements, group 1, group 2. Group 1, they have 1 valence electron. Group 2, they have 2 valence electron, 2 dots placed around the symbol. 13 to 18, how we find electron valence electron is important, please. We learn in chapter 5. Group number for P block, group number -10 equals the valence electron, equals the electron in the last S and P. 13 minus 10, 3. Boron, aluminium, gallium. So these are, they have 3 valence electrons. Group 17, which is very important. Group 17, they have 7 valence electrons. Group number -10 equals 7. they have 7, they have 6, they have 5, they have 4, group 14. Group 13, they have 3 valence electron. Group 2, they have 2. Group 1, they have 1 valence electrons. Electron dot notation is easy. This is for hydrogen and for nitrogen. We did it. Lewis structure, guys. To show the electron dot notation for molecules, how are we going to write electron dot notation for molecules? For electron dot notation for molecules called Lewis structures. Okay, what's Lewis structure? Are formulas in which atomic symbols represent nuclei and inner shell electrons. So how we're going to, for example, for H2, we have 2 hydrogen. Okay, it says symbol of the hydrogens represent inner. We have inner shell electron, we have nuclei. We don't represent this. The symbol represents the inner shell electrons and nuclei. And dot pair or dashes between 2 atomic symbol, we can write like that. This is dot pair. Pair means 2. The pair between what? Symbols, between 2 symbols, represent the electron pair in covalent bond or shared electrons going to be written between the symbol of the atoms. Or dashes, we can use dash, okay? H, a dash, and the other hydrogen. So this dash is same as the dots. Instead of dots, pair dots, we can write a dash. So a dash represents a pair of electrons, 2 electrons that have shared between hydrogens here. For F2, and it says while dot next to the symbol atoms represent unshared electrons. Look, if you write the Lewis structure for fluorine, both they have how many valence electron? Fluorine is in group 17, will be given in the exam, then means 7, 1, 2, 3, 4, 5, 6, 7. This ampere, there are 3 pairs, okay? 1, 2, 3, 4, 5, 6, 7. So these 2, they're going to share. Look, it's fluorine, they have 7 valence electron. These amperes, they are going to bond with each other, isn't it? To both have 8 electrons. So we're going to write like that. And these 2 dots, we're going to write like that. So 1, 2, 1, 2, 1, 2, 1, 2. So, or we can write like that. Fluorine, instead of these 2 dots or this pair of electron, we can use a dash. Okay, 1, 2, 3, 4. Okay, 5, 6, 1, 4, 5, 6. Okay, these are called what? Shared pair electrons. But what about these dots? They're called what? Unshared electrons, because they have not shared between the 2 fluorine atoms. So these pair, there are 3 pair. 1 pair means 2 electrons. So there are 3 ampere. Okay? There are 3 pair of electrons and they are unshared. But these are shared electrons. Look at for chlorine. 2 chlorines, they have 7 valence electrons and they are going to share 1 electron each. So what happens? We can write Lewis structure like that. They are going to share these 2 dots. The shared electrons are going to be written like 2 dots or a dash between the symbols, and the unshared electrons going to be written next to the symbol. So unshared electrons, we call them what? Lone pair. 2 unshared electrons together, they make a pair, and they are unshared. We call them lone pair or unshared pair electrons. So each chlorine has 3 lone pairs. It's important, guys, to know lone pairs. Lone pairs, they are electrons which are not shared between 2 atoms. Each chlorine here has 3 pair of electrons. 3 lone pairs means 6 unshared electrons, or 3 unshared pair electrons. Okay, but these are what? These are shared pair. There's only one shared pair, can be 2. Okay, it's common to write Lewis structure that show only the electrons that are shared. Look, we have another way to write Lewis structure, which is called a structure formula. A structure formula, we're not going to show the unshared electrons. We remove from this formula. For example, chlorine, this is the Lewis structure of chlorine. If I want to write a structure formula, I'm going to remove the what? Remove the dots. Means what? The unshared electrons. Unshared, I'm not going to write unshared electrons. And the shared electron we're going to written by a dash. We're not going to use dots. Okay, this is what? This is a structure formula. What structure formula? Indicates the kind, number, arrangement, bonds using dashes. Okay, to represent bonds, but not what? Not the unshared pair of atoms in a molecule. We're not going to show the unshared pair of electrons. We're going to remove. This is Lewis structure. This is structure formula. Okay, that's it. Structure formula is Lewis structure, but we're not going to show the unshared pair of electrons. That's it. That's it. Now, if we want to draw Lewis structure of a molecule which is not diatomic molecule, because in this slide, you know, we did for hydrogen, fluorine, chlorine, these 3, they are all what? Diatomic molecule. Well, if we write Lewis structure for a molecule which is not diatomic molecule, it's different. So let's use, there are steps that we need to do before draw the Lewis structure, Okay. We have iodomethane. How we're going to do it? First of all, if I give you a molecule in the exam, first of all, think what? Like that. Determine the type and number of atoms. Here we have type, we have carbon, hydrogen, iodine. Number of atoms. We have 1 carbon, 3 hydrogen, 1 iodine. Look, Lewis structure. In this section, we do just for molecular compounds, for molecules, okay? Not for any compounds. It means they are, in the molecules, they are all made of nonmetals, okay? Carbon, hydrogen, iodine, also they are all nonmetals. We did the first step. Then write electron dot notation for each type of atom in the molecule. Let's do it for carbon. In the exam, I tell you carbon is in group 14. You must know that when we say group 14 means it has 4 valence electrons. So 4 dots, okay, around this symbol. That's it. Hydrogen is in group 1, only 1 dot. And we have iodine, which is in group 17, 7 dots, 1, 2, each side give 1. Okay, then give other sides to make the amperes pair 7. Okay, this is electron dot notation for each type. But we know there are 3 hydrogens, We just do it for 1. Next step, determine the total number of valence electrons available in atoms to be combined. Number of valence electrons that the atoms they have in this molecule. How we know? We have 1 carbon, right? 3 hydrogen and 1 iodine. Together, 1 carbon, 4, 3 hydrogen, 3 dots, 3 valence electron. So 3 plus 4, 7. Iodine has 7 too. 1 iodine means 7 valence electron. Totally 14. We can do it like that. Okay. We have carbon, 1 times 4, 4 valence electron. 1 iodine, 1 iodine. 1 iodine has 7. 7 equals 7 valence. We have 3 hydrogen. 3 hydrogen. Each hydrogen has 1 valence. So equals 3 valence electron. Total, there are 14 valence electron. Atoms of this molecule, totally they have 14 valence electrons. Okay? This step is important you to not lose any electrons in the Lewis structure. Okay? Total, there must be 14 valence electron when you draw the Lewis structure. Okay. Next step, central atom. It's very important you to know how to indicate a central atom. Central atom, look, it says, this next step, arrange the atoms to form a skeleton structure for a molecule. If carbon is present, it's the central atom. Otherwise, the least electronegative atom is central, except for hydrogen, which is never central. First, you must know, if there is carbon, carbon is central. If there is no carbon, the least electronegative is central. And next, you must know hydrogen is never going to be central. How we know that the least electronegative atom, the one that's from left of the molecule, is the least electron, is going to be central. Okay? The carbon is always same. But if hydrogen is from left, no, hydrogen is not going to be central. Like in H2O, you say, teacher, you said the one that's from the left is the least electronegative and is going to be central. But for hydrogen, it doesn't work because hydrogen never is going to be central. Okay. Then connect the atoms by electron pair bonds. Next, I'm going to make these 2 points together. Look, we have, this is carbon. Carbon is central. Basha. When you say central, other atoms, they surround the central. They make bond with the central atom. So, carbon is central, and we have 3 hydrogens. 3 hydrogens, they what? They surround the carbon, which is because carbon is central. And we have 1 iodine. Don't forget to write the electron dot notation next. Some students, they make mistake here. Not mistake, that they get confused. Try to put the ampere, these are pair, in the side, in that side that faces the central atom. Don't put hydrogen here, okay? Just write in this side that faces the central for this hydrogen too. Look, then it says connect these atoms by electron pair bonds. Okay, look. Next step, you must know how carbon becomes 8 valence electron, because we know atoms, they are going to bond to have 8 electrons in the last show. So carbon, it bonds with 3 hydrogen, 1 iodine to have 8 valence electrons, right? How it can have 8 valence electron? By sharing electron with another nonmetals, because it's molecule, right? It's between nonmetals, so there's always sharing. How? It needs 4 electrons, means it must share 4 electrons to be 8. It must make 4 bonds. Hydrogen, we know its exception. It has 1 electron, and to its last shell be filled, it needs 1 more electrons. Means each hydrogen needs one more electron. So each hydrogen is going to make a bond. So we're going to do what? Get ampere electrons between two different atoms. We get these two the ampere electrons together to become pair, and when they become pair, it's going to be a bond. Okay, so here let me use different color. These two, they get together. Ampere ampere to be pair. Okay, to be a bond. Each hydrogen needs one bond. It makes bond with central, not with another hydrogen. These two, they make a bond. Carbon has made 2 bonds until now, but it needs 2 more bonds to be 8. It makes a bond with this hydrogen too. And iodine has 7 valence electrons. It needs 1 more electron, so it needs to share 1 electrons. So carbon also needs 1 more bond. So at this time, both of them, they're going to share their ampere electrons. And ampere electrons, they're going to be shared, not pair. Pair, they're not going to be shared. So what's going to be? Okay, how we like draw the structure. 2 dots here for this one. Dots next to between these symbols represent the shared electrons. And for iodine, okay, and don't forget the ampere, the lone pairs, okay, unshared electrons. And these 2 dots for this hydrogen, because now they are shared. And another hydrogen, 2 dots. Okay. Or instead of pair electrons between the symbol of 2 atoms, or instead of shared electrons, we can represent by dash. Okay, hydrogen. Instead of these 2 dots, we can use write iodine like that. Don't forget the lone pairs. Iodine has 3 lone pairs. Hydrogen, and another one is hydrogen. So this is the Lewis structure. There are 2 methods to write Lewis structure for iodomethane. Okay. Now at the end, each carbon has how many valence electron? 2, 4 is. Carbon has how many valence electron? 2, 4, 6, 8, right? 2, 4, 6, 8. Iodine 2, 4, 6, 8. Okay, and also we can do here. Each dash represent 2 electrons. 2, 4, 6, 8. Iodine has how many valence electron? 8 also. Each hydrogen has 2, 2, 2, 2. Okay, that's it. Let's do it for NH3. NH3, ammonia, we have 1 nitrogen and 3 hydrogens. 1 nitrogen and 3 hydrogens. Okay. Then total number, write Lewis structure for each type. For nitrogen, it's in group 15. I will give in the exam 1, 2, 3, 4, 5. Hydrogen, we have hydrogens, it has 1 valence electron. We have 3 hydrogen. So total we have how many valence electron? 5 plus each hydrogen has 3 electrons, 8 electrons. Now, which one is central? Hydrogen is never going to be central, so nitrogen is going to be central. Okay. Nitrogen central. 1, 2, 3, 4, 5. We have 3 hydrogens. These 3 hydrogens, they surround the the central atom. Where should we write the valence electron, the dot of valence of hydrogen from this side that faces the central? Okay, another hydrogen. And next to the amperes, don't write the H here. that faces the central, the pairs, because unpairs they bond. Okay, now nitrogen has 5 valence electrons. To be 8 needs 3 more electrons. Means it must make 3 more bonds. When how many electrons does it need to be 8? It makes the number of bonds that's going to make equals the number of ampere electrons too. Okay, now these it has one, these two, they can make a bond, and nitrogen can make a bond with hydrogen. It has this ampere and this ampere, they can make a bond, or this is a bond, and these 2 amperes, they can make a bond to be pair. These 2 also, they make a bond. Now what's going to happen? This is the Lewis structure, or we can use dash. Okay, these 2 make a bond. Okay, and this, okay, this is another bond, and this, okay, it's not hydrogen, and these 2 dots, they are lone pairs. Don't forget to write it. This is Lewis structure. If I tell you write structure formula, don't write these 2 dots, the lone pairs, because they have not shared. We must write it again. Okay, that's it. Now nitrogen has how many valence electron? Each dash represents 2 electrons. So 2, 4, 6, 8. Okay, each hydrogen also has 2 valence electron, and the total number of valence electron in this molecule is 2, 4, 6, 8. Okay, that's it. What about let's do it for H2S. H2S, which one is going to be central? Sulfur. Sulfur is in group 16. 1 means 6 valence electron. 1, 2, 3, 4, 5, 6. And hydrogens, they surround the sulfur, and write the hydrogen next to the ampere. So now sulfur, it has 6 valence electrons. To be 8 needs 2 electrons, so it's going to share, it's going to make 2 bonds. By making 2 bonds, sulfur is going to have 8 valence electrons. Also hydrogen also always make 1 bond. Pasha, these 2, they make a bond. These 2, they make a bond. Okay, now sulfur, it has 8 electrons. We can write Lewis structure. Sorry. So these 2 dots uses for hydrogen, and okay, another bond here, and don't forget the lone pairs. These are lone pairs, and these are the shared pair. Okay, so now sulfur has 8 valence electron, and each hydrogen also, it has 8. We can also write like that. This is the 2 methods to write Lewis structure, which this one is very common. Okay, that's it. Okay, multiple covalent bonds, single, double, triple bonds. What's single bond? Is a covalent bond which one pair of electrons is shared between 2 atoms. When one pair of electrons, one pair means 2 electrons, is shared between 2 atoms, it's called single bond, like H2. Okay, here how many? Only 1 pair is shared. Okay, a dash, 1 pair means only 1 dash, a single bond. What about double bond? Is a covalent bond. Look, they are all covalent bond, single, double, and triple, because between metal and non-metal ionic bonding, we don't have single, double, and triple. Okay, double bond is a covalent bond which 2 pair of electrons are shared between 2 atoms. 2 pair What does it mean? 2 pair means 4 electrons. Okay, like that. 2 dashes. 2 pair, 4 electrons. Okay, C2H4. If I tell you in the exam, write Lewis structure for C2H4, okay, and I might ask how many double bonds are in this molecule. How you know? Look. Or what bond is between carbon in this molecule? Single, double, or triple? You can ask like that. So C2H4. Which one is central? Carbon or hydrogen? Carbon. Carbon is always central. We have 2 carbon, so both of them are going to be central. We have 4 hydrogens because both of them are central. So each carbon is going to be surrounded by what? By 2 hydrogen. And this carbon is going to be surrounded by 2 hydrogen. Write electron dot notation. Okay, good. Okay, for carbon, 1, 2, 3 carbon in group 14 has 4 valence electron. Okay, look. Now, each carbon needs 4 electrons to be 8. Each hydrogen to be 2 needs 1 electron. So each carbon must make 4 bonds. How? By getting when amperes they get together, they make a bond. So this is carbon can make a bond with this hydrogen, this carbon. This carbon can make a bond with this hydrogen. Also for this carbon is surrounded by 2 hydrogen, means these 2 hydrogen they make a bond with this carbon. So this is a bond. These 2 make a bond. Now, each carbon has how many valence electron? This is 2 because it has shared 1 electron with hydrogen. These 2 electrons, they are the electrons of both. 2, 4, 5, 6. 2, 4, 5, 6. Each carbon now it has 6 valence electron. To be 8, they must have 2 more electrons. So they must make 2 more bonds. They must share 2 more electrons. So look, this is each carbon has 2 amperes. So these 2 amperes they can make bonds. This is a bond, and these 2 also they can make a bond. Now how we're going to write? We have between carbon we have how many? We have 2 bonds, 2 dashes, isn't it? And for hydrogen, this is another bond. Here for this hydrogen we can use a dash. Okay, this is like that. That's it. So now we have double bond between carbon and carbon. Between carbon and hydrogen we have single bonds. Okay, that's it. Triple bond. What's triple bond? Is a covalent bond in which 3 pair of electrons are shared between 2 atoms. 3 pair of electrons are shared between 2 atoms. 3 pair of electrons means, okay, 3 pairs means 6 electrons, or 3 dashes. 1, 2, 3 means how many? Each dash represents 2 electrons. 1 pair. Okay, that's this triple bond. Example, nitrogen. We have triple bond between 2 nitrogen atoms. N2 is a diatomic molecule, isn't it? Let's explain. We have 2 nitrogen. Which one is central? None of them, or both of them. So when there are 2, none of them is going to be central. They're going to bond with each other. So both they have 5 valence electron, both, because nitrogen they are in group 15. But each nitrogen has 5 valence electron. So to be 8, they need 3 more electrons. So they must share 3 electrons. So they have 3 amperes, so they can make 3 bonds. What happens? The amperes, they get together to make bond. These 2 amperes, they get together to make a bond. These 2 amperes, they get together to make a bond. And these 2, they get together to make a bond. Okay, now by making 3 bonds, each nitrogen going to have 8, 1, 2, 3. So there are 3 bonds between nitrogen and nitrogen. Now both they have how many valence electron? 8. 2 plus 2, 4 plus 2, 6 plus 2, 8. Now 2 plus 2 plus 2 plus 2 equals 8. Both they have 8 valence electron. Both are stable. Okay, that's it. For C2H2, we have 2 carbon, both central. We have 2 hydrogen, each carbon, because both are central. Each carbon will be surrounded by a hydrogen. Write electron dot notation. Sorry. Yeah. Okay, 1, 2, 3, 4. 1, 2, 3, 4. 1, 1. Each nitrogen must make 4 bonds. It makes a bond with this hydrogen and a bond deck. So also this carbon make a bond. Each carbon has made 1 bond. Because carbon always make 4 bonds to be stable. Each carbon has made a bond. So each carbon, they need 3 more bonds so they can make bond with each other. So these 2 amperes, they make a bond. These 2 amperes, they make a bond. These 2 amperes, they make a bond. Now we have triple bond between carbon. Okay, that's it. So we can write Lewis structure for C2H2 like that. Here these must be dots. Okay, dots, not line, because this, when we use dots for sharing electrons, these must be dots too. Double and triple bonds are referred to as multiple bonds or multiple covalent bonds. We call them what? Multiple covalent bonds or multiple bonds. So double bonds in general, double bonds, they have greater bond energy and they are shorter than single bonds. And triple bonds are even stronger and shorter than single and double bond. What does it mean? Means, look at here. Which bond is strong? Triple bond. Strong increases, down and is going to decrease. So triple bond is stronger than double. Double is stronger than single. Okay. What about bond length? The triple bond is very short and is shorter than double. Double is shorter than single. Single is longest, right? So you must know that which bond is very strong. Triple, there are 3 bonds. So when there are 3 bonds, so the bond is very strong, you need higher bond energy. Look at here table 2. Between carbon, the average bond length is 54, sorry. Okay, for carbon 134. For carbon, when there's a triple bond, is 120. Look, when the number of bonds increase, the bond energy the bond length decreases. Okay, when the number of bonds increase. So we can say triple bond is the shortest bond. And bond energy, so when there is a single bond Between carbon we need 346, but when there's a double bond we need high energy. We know that bond energy is the energy you need to break a bond. When the bond is strong, you need high energy, right? So for triple bond between carbon we need 835 kilojoule for each mole. Okay, so you must know that triple bond is stronger than double, double is stronger than single. And for the bond lengths, triple bond is the shortest, then double, then single bond. Okay, draw the Lewis structure for CH2O. I think we can do it, but actually I want to do it for CO2. You can do it. For example, we have for CH2O, write Lewis structure for each, find the total number, and carbon is central. Okay, carbon central, and hydrogen and oxygen, they surround the central. We have 2 hydrogen and we have 1 oxygen. Okay, oxygen, they have 6 valence electron. So now carbon needs 4 bonds, but there must be 1 electron here. So these two, they make a bond. These two, they make a bond. This is 2 bonds, 3 bonds, but also these two, they can make a bond. So there will be 3 double bond between carbon and oxygen. Okay, and there will be a single bond between carbon and hydrogens. Okay, that's it. For CO2, which one is central? Carbon is present. Carbon is central. And we have 2 oxygens. 2 oxygens, they surround the carbon. Each oxygen has 6 valence electron. Okay, that's it. These two, they make a bond. Carbon must make 4 bonds. Each oxygen can make 2 bonds. Okay, done. This oxygen, these two, they make a bond, and these two, they make a bond. Okay, now between this carbon, okay, we have double bond between carbon and oxygens. Okay, and okay, another double bond. Sorry, there, you must delete this one. That's it. Carbon has 2, 4, 6, 8. Oxygen 2, 4, 6, 8. This oxygen also 2, 4, 6, 8. Now they're stable. Okay, you can do it for another one that is made of 1 hydrogen, 1 carbon, 1 nitrogen. Carbon is central, and nitrogen and another hydrogen will surround the central. Okay, and nitrogen must make 3 bonds and carbon must make 4 bonds. So carbon make a bond with this hydrogen. It must make 3 more bonds, so it makes 3 more bonds with 3 nitrogen, with 3 electrons of nitrogen. Nitrogen also must make 3 bonds. So these two make a bond, these two make a bond, and these two, they make a bond. So it's going to be carbon, triple bond between carbon and nitrogen. Don't forget the lone pair, and it will be like that. Okay, that's it. This is the section review, and the answers you can check by yourself. Okay, thank you for listening. See you next time. Bye.